Okay.
So Eileen, you're the only student that showed up so far. Except people are the students.
Okay, so welcome to the IMA Data Science Seminar. So I'm very happy to have Vlad Kobzar here to talk today. So Vlad got his PhD at NYU Current in 2021, and he's a postdoc at Columbia University. So his research interests are sort of at the intersection of PDEs and data science, and he works on online learning problems and inverse problems. And today he's going to talk to us about a PDE-based analysis of the symmetric two-armed Bernoulli bandit. Okay. And for those of you on Zoom, feel free to type questions into the chat box during the talk or afterwards as well. Okay, so please.
Thank you very much, Jeff. Thank you very much, Gilad. Will, are other people who organized the talk? Very glad to be here. My talk will be fairly informal, and the mathematical exposition is more or less elementary. So please feel free to, if something is not clear, it's probably me. So please ask questions. Okay. So this is so the title is PDE-based analysis of the symmetric two-armed Bernoulli bandit. This is joint work with Bob Cohn. So I will give you a background about this learning problem. We will establish the minimax optimal player for that problem. And then we will provide a PDE-based characterization of the value function of this problem, which is called regret in the literature. So just to give you some background and motivation, it's called bandits from the slot machine analogy, where a player decides which arm to pull from the multiple arms. The player observes the rewards from the arms that's been pulled, does not observe the rewards from the other arm. So, in a sense, you could see that it's an incomplete information problem, and the player needs a policy in terms of deciding which arm to pull based on the previously observed reward. So that's a setting. You could maybe to show another motivation, just to contrast this problem with A/B testing and hypothesis testing. This is a historical context where this problem has been used. So if you're talking about just plain A/B testing, you're considering a new drug. So let's call it arm 1, and arm 2 is the old drug or a placebo. You fix your total sample size, which you, in some randomized fashion, distribute between the population that gets drug 1 and the population that gets the new drug and the old drug. You have a hypothesis that your null hypothesis is that the chances of recovery of the new drug are lower than the chances of recovery if you took old drug or placebo. It's relatively standard to form a test statistic, which is a function of sample means of the arms normalized by the variance. If you're assuming the two arms to be Bernoulli random variables, and you reject the hypothesis if your z statistics exceeds the threshold corresponding to whatever p-value you want to do. So this is shown for 5% p-value, right? So Thomson in 1933 considered a context where, let's say your data so far suggests that the new drug is better, but it is not conclusive as defined by p-value less than 5%. So the question is, should we adjust our actions to minimize the administration of the inferior treatment? And the heuristic he proposed is that if you're 90% confident under whatever confidence measure that you're using, then you would allocate 90% of the trials to the new drug. And as you conduct more trials, this percentages will adjust accordingly. So what in the, so you if you so this type of method raises the trade-off between exploration and exploitation. So in the basic A/B testing, in the beginning, you engage in pure exploration to understand how good your drug is. And then after that, you've got an FDA approval and you're doing exploitation, versus a bandit selection where you are simultaneously deciding between choosing the best action given the data that is revealed so far, but you're also choosing the best action to improve your knowledge about the values of the different actions. So the bandit selection that was that I'll talk about entails, we will not study this particular trade-off, but in the motivation is to understand, among other things, the trade-off between these extremes, as well as a desire to minimize the administration of the inferior treatment or to minimize the amount of times you would pull the arm that inflicts higher losses on you. So formalizing this two-armed. So are there any, maybe let me just ask you, is there any questions about the setup? So you could formalize this problem as a two-arm Bernoulli bandit. The safe arm AJ, where J is secret from the player, is a probability distribution given by Bernoulli probability distribution, where probability of 0 reward is 1 minus epsilon j over 2. Probability of 1 reward is 1 plus epsilon j, and the risky arm is the same with a different parameter j. So it's risky because epsilon I is smaller than epsilon j, so the expectation of the safe arm is higher. The expected rewards from the safe arm are higher than the expected rewards from the risky arm. And so this is fixed. This j is determined somehow in the beginning of the game. We'll talk more about how it's determined. And in each, so it's a sequential the decision-making process where at each time period from minus capital T to -1. So I will use the negative time convention because it makes for me at least, the bookkeeping and then making connection to the final value problem in PDE a little bit easier. So just bear with it, but it's but we're talking about capital T number of prediction periods. It's a discrete game. In each period, the player selects a probability distribution over the arms using all the information that's been revealed to her. The rewards from each arms are sampled from these two probability distributions. Then the player choice of the arm is sampled from the distribution, so the player can randomize. Their arm, that the index of the arm IT that's been sampled and the reward of the chosen arm GT IT are revealed to the player. So in this context, the arm that the player didn't choose, so there are two rewards. The player chooses arm IT, whichever one it is. The other arm is not revealed, so the player doesn't know what the other game is. Are there any questions? Okay, so how
can you just maybe say, you say that J is not known. So what is J in the bandit? Just so I understand the motivation.
Oh, J is just the arm that has higher mean. So the arm that you would like to play all the time, right? So you have two arms and you're just trying to decide which one is better, which one have. I mean, it's optimistic to say higher rewards, maybe just the one that inflicts smaller losses on you.
Thank
you. Okay. Any other questions? You could generalize it to to more arms, but in this particular setting, you're just talking about 2 arms, yeah. I'll talk a little bit more about connections to multiple arms. So then, so how do you measure what is the player's objective? So to do that, we look at the final time expected regret, which we'll simply call the regret. It's associated with a given policy, which is a recipe, a probability distribution at each time period that the player determines based on all the information that's been revealed to her. And the regret, the final time expected regret of a given policy and from a distribution that I defined previously, which is indexed by J. One of the arms is safe. J is the index of the safe arm. You look at the difference in each period between the case arm and the rewards from the case arm and the rewards from the arm that's been sampled by the player. So this keeps accounting for k equals 1 and 2, how well the player did in that period. If relative to each arm, then you sum it up. You take the arm that has higher gains, so the better arm. So if you maximize over k, you end up comparing the player's performance against the best arm in hindsight. And then you take expectation with respect to the randomization of both the player and the arms. Okay. Any questions? And you could, yes.
The expectation over epsilon I, epsilon j. So what is the expectation over?
The expectation of both the player strategy is randomized. So your so IT is a random variable that at each time period it's a sample from a distribution PT from the players. So that's one source of randomness, and then the other source of randomness is the arms themselves. They're Bernoulli distribution. So AJ encodes the 2 Bernoulli distributions. Okay. Any other questions? So you could just come up with some notation that makes this accounting a little bit more concise. You have X is the accumulative vector valued regret, where you just sum up this quantity, but it's a vector in this case. In Rx is a vector in R2. So the case component of this vector just tells you how well over the entire prediction period the player does relative to arm 1 and relative to arm 2. And then you just, a maximization still entails taking the better of the 2 arms. This is just the instantaneous regret. This is just the vector of all ones. So at time tau, this is GI tau, the gain of the player. And then this allows you to compare how player does relative to both arms. So just to, yes, please.
What is the T in bracket minus T?
Oh, so this is just a summation over all the time periods from minus T to minus 1. So it's this summation. So I just wrote it like this. Thank you. That's a good question. And I should have made this clear. But it's a sum over all periods. So in the hypothesis testing framework, the regret represents the expected difference between the outcomes from the better fixed treatment in hindsight relative to the sequence of treatments chosen by the player, right? So, okay, and then there's another quantity which is different but related, which is called pseudo-regret. And pseudo-regret, so we can define it, maybe it's even simpler, easier to see what's happening. So if you take the gap between the arms means, denoted by epsilon. So sorry, before I used epsilon j and epsilon I, so I've overloaded the notation a little bit, but from now on, epsilon is just the difference between the means of the two arms and the final time expected pseudo regret. Again, you fix a player's policy, you fix the distribution of the arms, you fix which arm is safe, which arm is risky, and so the pseudo regret is determined by the number of times the risky arm was pulled, again in expectation with respect to the player's randomization times the epsilon. So every time you pull a risky arm, you get penalized by epsilon. And in the hypothesis testing framework, the pseudo regret represents the expected number of times the inferior treatment is chosen. You could see it's different. This has more randomness because this encompasses the randomness not only from selecting the inferior versus the good treatment, but both the inferior and the good treatment come with their own probability of successes. So this kind of quantity regret encodes this randomness that you could have good or bad outcomes from either the risky or safe arm. This just focuses on the expected number of times the inferior treatment is treated. And you can rewrite this expression. You could expand epsilon, and you can rewrite it again in terms of this variable x, vector valued regret, at final time. And it has the same expression as the regret, except that the max and the expectation are interchanged. So from this computation, we know that the pseudo regret lower bounds the regret. So they're related. Okay. Okay. So then let me talk about min-max regret and min-max optimal player. So so what we want to do is we want to define a min-max optimal player. It is a minimizer of the minimax regret or pseudo regret, and that quantity is defined. So previously in this setting, we defined this is a maximization at final time, but there's also kind of a maximization at the beginning. When the player chooses its policy, the adversary commits to choosing which arm is risky, which arm is safe. And so in this setting, min-max regret is so first you have a minimization over P of the max over the two arms. So the player wants to choose a policy in this setting that works as well as possible against the arm that inflicts the highest regret on her. Yeah. Yes, exactly. Exactly. So that max is at the inside the expectation. This is at the final time. So this represents the final value, the quantity. This max is in the beginning of the game, sort of outside. So the way this game works is you, in the beginning, the adversary determines, knowing the policy, right? Because the maximization is after the minimization. So here, given this policy, the adversary picks the worst arm, and then at final time, you look at sort of what happened. And so this maximization just tells you what happens at the final time. So so that's right. So it is well, this is a discrete, right? This is a discrete game, and That's a good question. So I don't know if it has to. Yeah, I don't. Yeah, it's a good question. You're not. So I'm not exchanging. I'm not interchanging max and min. It's not going to work if it's going to be trivial.
The player knows the.
Yeah, the player knows that that will be trivial. You would pick it exactly. So that we're not doing the min in this setting. Min max is not equal to max.
I'm just kind of looking if you have kind of
Well, so these are bound. All of these sets are bounded in a way that this game runs for a finite number of periods, right? So P is a just a discrete probability distribution over all arms. All the rewards are bounded, so it seems to be possible to do it. It's a yeah. Okay, great question. I'd love to talk more about it.
It's supposed to be harder to set up here to actually find options.
It is hard to find. Yeah. Exactly. Okay. Please also ask questions. It's a great question. Okay, so okay, so then so what makes this problem hard is that in min-max setting, as opposed to Bayesian setting or something else, the probability, the player in principle can use all information available to her from previous periods, right? So it's a function of history. History are all the prior samples of the arms, all the previously revealed rewards. So it's a very large tree, and it's a very difficult problem. So let me just tell you what is known about it. So it is, as I mentioned, one of the oldest learning problems. There are asymptotic bounds that are given only on pseudo regret, which in this case, what we know is that the pseudo regret grows as square root of t, the number of time periods. The precise constant is not known, but it was relatively early. It was known what the bounds are by picking specific policies for the adversary, specific policies for the player. It was possible to bound the pseudo regret. Yes.
What are those numbers? Like what I mean, 1.306. What is it?
Oh, it's a constant. It's a prefactor of the leading order term of the regret.
Sure. What is it? What does it represent? I mean,
it means that you would select the inferior treatment. So if you're doing this process for capital T time periods maybe in the A/B test or in the drug trial test, you would select the inferior treatment. More than there's a distribution of the arms that will guarantee that for any policy, the player will make a mistake, will select the inferior treatment at least 0.6 times square root of t times. But there's also a player strategy like the Thompson sampling that I described before, which guarantees that for any distribution of the arms, the player will not select the inferior treatment more than 0.376 times square root of t times.
Right. I guess what I ask is, where does this particular number come from? Like, is there?
So they instantiate. They do a probabilistic calculation where they say, okay, to get the lower bound, I just want to prove that there's some distribution of the arms. So they pick that they carefully pick that distribution of the arms, kind of balancing on the one hand. So you don't want to have the gap too large because the gap could be easily discovered, but you don't want the gap to be too small because if the gap is too small, then you don't inflict high regret. So you sort of do this calculation, and they did some calculations like that.
So there's an explicitly solvable, explicitly.
It's
computable model
it's
behind
not it's
it.
so this is not so well, and it's asymptotic, so it's not so well defined, but the only explicit lower bound is, this is what I'm going to talk about, the only kind of crisply defined lower bound in the literature. Okay, great question.
Zoom, so they can't hear other people in the audience because we don't have good microphones.
Oh, so I will repeat the
So,
questions. So yes. So okay. So the question before was what do these bounds represent, and in what cases they're instantiated by a specific policy. Okay. So then there's also non-asymptotic bounds. They're also available for K-arm bandit. Obviously, the constants will depend on K. And so these bounds are available both for regret and pseudo regret, and they're given as follows. Okay, so the exact constants are still unknown, but this lower bound, which is the only lower bound in the literature for pseudo regret, and therefore for regret by the inequality that we've shown previously, for both stochastic case where the arms are IID, for adversarial, this is the only lower bound that's out there that is explicit. And so we will look at that, the restriction of that lower bound policy for two arms, which is the symmetric two-arm bandit. Okay. Maybe I'll ask if there are any other questions.
Very simple. Why the bounds is different from the rate?
Yes. So there's just more like the regret encodes more variance, because this also encodes like you could still end up with bad outcomes if you select the arm that the safe arm. So this encodes kind of more variance. That's essential. Any other questions? Okay, so the symmetric two-arm banded. We did more or less the same thing, except that the means of these two arms are symmetric around 1/2. Here you get the reward U of 1, which is probably 1 plus epsilon from safe arm, and from the risky arm you get the probability of reward of 1 minus epsilon. Right. So this is so I'm just defining the lower bound. I'm defining the strategy for the adversary that achieves the only known lower bounds. And this is just a restriction to two arms for simplicity. Okay. So the rest is the same. The rest of the problem is the same. Okay. So previously, even in the symmetric case, not everything is known. So this was looked in 1983, where they looked at the Bayesian version of this symmetric two-arm bandit problem. So it's the same as above, except that the index of the saved arm is sampled from the uniform distribution over two arms. You could think about, in the hypothesis testing framework, you could think about the prior distribution as assigning equal probability to the hypothesis of one arm being saved versus the other arm being risky. And the Bayes optimal player is a minimizer of the Bayesian pseudo regret, which is this quantity. It's the same as the min-max regret before, except instead of the inner minimization over which arm is safe, which arm is risky, you just take expectation over the two arms. So this is just the expected number of times the inferior treatment is chosen under uniform prior, not under the min-max assumption. Okay, so that's really the only, and as we said before, in general, good players balance sampling of the arms was choosing the arm with the highest expected reward. But in the symmetric case, the distributions of the two arms are statistically equivalent in the sense that for either choice of safe arm or risky arm, A1 is equal to 1 minus A2. So if you think about these as random variables that are distributed according to the law, the Bernoulli law, so the player will get the same information about the means of both arms by sampling either one. So here the Bayes optimal player is myopic. It chooses the arm with the highest posterior probability of being the safe arm given the revealed rewards. Okay, so but even though exploration in this setting is not needed, even this problem has not been fully understood. So here's what so this is the Bayes optimal player that's been computed explicitly. So it chooses arm 1 if this quantity is greater than 1. So this is cumulative rewards from arm 1, revealed reward. There's a cumulative rewards from arm 2. These are the number of times arm 2 has been sampled, this number of times arm 1 is sampled. If this quantity is 0, then you just allocate the same probability to both arms, and it's 0, 1 in this case. And I will show you how you get this number in a minute. But in 83, Bather determined the leading order of Bayesian pseudo-regret, which is this quantity. So finally, we have the optimal leading order. Sorry, we have the leading order term of the optimal regret here. Again, no non-asymptotic guarantees. We don't really know in what scaling, are there any, in what regimes this works, like how exactly the error scale. So this is just computation of the leading order term. And so what we did is we proved the min-max optimality of PM. So that's a separate proof that's is not PDE-based. But then once we know the optimal player, we have been able to pose a dynamic programming problem and associate the leading order term of the min-max optimal regret and pseudo-regret with explicit solutions of linear parabolic PDEs. And so in this work, we both unified Bayesian and min-max regret, because to compute Bayesian regret, you don't need this step. You just prove whatever you find Bayesian optimal player. You don't need the min-max proof. You could still put in our PDE. This quantity will come out of our PDE methods. And we also unified the analysis of regret and pseudo-regret by varying the final value of the problem. So there's some also more technical contributions. So this policy is discontinuous as a function of revealed gains, and the number of times the arms are sampled. So it has a discontinuity when this quantity is 0. So the spatial derivatives of the solution of the relevant PDE are also discontinuous in this region. If you keep this discontinuity epsilon small, it doesn't affect the leading order behavior, but it affects the discretization error. So we're actually able to optimize this discontinuity to minimize this error. And we explicitly determine the leading order terms of regret and pseudo-regret, i.e. the exact constants in front of square root of t in the symmetric bandit setting. So the existing techniques rely on non-constructive information theoretic proofs to get the bounds below on the pseudo-regret, which and this, as I mentioned before, leads to the only known non-asymptotic lower bound in the general bandit settings. Our results lead to sharper non-asymptotic regret and pseudo-regret lower bounds in the two-armed case, and they're established by very transparent elementary methods that don't, basically undergraduate, more or less undergraduate math. Okay, so extensions. So of course, general bandits are, so I'll talk about sort of why this is a useful result beyond the setting we looked before, and then I'll talk about proof techniques. So, and I have until the 25, I have, okay. So General bandits are more challenging, of course, due to the exploration exploitation trade-off, but there are more realistic settings where exploration is not needed. And so we expect our work to be immediately extended. So for example, the literature establishes that in the Bayesian K-arm bandit setting, where the player knows that one arm has an arbitrary distribution P and doesn't know which arm, and all the other arms have the same distribution Q, you don't need, in this setting, myopic policies that maximize the posterior probability are optimal. So there's been a line of work sort of going back to David Blackwell and his PhD students. And this is the case. In fact, this is the lower bound for K-armed, for general K-armed bandits. So if we study this problem, we can improve the lower bound for the general bandits as well. And also our techniques could be used in the settings where, in general bandit problems, where a possibly suboptimal policy is given, so such as Thompson sum. Okay, so what are the main ideas? We can dramatically simplify the state space of this myopic player by centering the arms. So we would, in fact, that would eliminate the dependence on this SI, the number of times the arms were sampled. So what makes this proof difficult is that an optimal strategy can depend on all available information at time, that is all the history. Therefore, we cannot in the min-max setting use dynamic programming directly, because you would need to, at each step, optimize over history. So your state space is enormous and there's no hope of getting a PDE. But we developed a novel iterative proof that addresses this issue, but it is conceptually similar to dynamic programming. So let's just look at the centering and this proof in a little bit more detail. So in the machine learning literature, this problem is usually studied with 0-1 gains. And the Bayes optimal player that minimizes the posterior probability can be computed directly. So pi I is the likelihood of observing a given configuration of gains if the ith arm is safe. And you could, just from Bernoulli mass function, you can compute it. So it's this quantity. So there's a lot of cancellation. So this is where this quantity 2gi minus 2g1 minus 2g2 plus s2 minus s1. This is where this quantity comes from. So if this quantity is positive, since epsilon is positive, P1 has a higher posterior, etc. Okay, so if we just rescale this, so we look at the centered rewards from -1 to 1, we just multiply it by 2 and then subtract vector roll ones. And then we get cumulative gains, cumulative centered gains from each arm. CR is their difference, R for revealed. And the myopic player, after the centering, simplifies dramatically. You don't need to keep track of S. And you could just see that by an algebraic calculation. So if you center the gains, you have these ones times the number of times the relevant arm was pulled, and that cancels with this guy, which just counts the number of times each arm was pulled. So this is very simple. The harder proof is once you have centered, you still need to prove the min-max optimality. But here the idea is that now you have symmetrized the arms. So if G is a trial from one arm, then minus G can be viewed as a trial from the other arm, again, because of this, because of the symmetry of the distributions. So you can convert observed trials from arm 1 to trials from arm 2. You could see that the sample mean of the resulting gains of arm 1 is positive exactly when this quantity is greater than 0. So it's a maximum likelihood estimator. So arm 1 is more likely to be safe if CR is greater than 0, vice versa. If CR is less than 0, no distinction is possible. If CR is equal to 0, And since the gains are independent, the order in which the arms are chosen is irrelevant. So it's difficult to imagine how a different strategy could do better. But again, this is not a proof. This is just the intuition. And the proof, it's still a fairly involved proof because you have to consider this very large tree and all the history. But the basic idea is to start with a min-max optimal policy, construct a new strategy such that if there's a time tau, the earliest time where the optimal strategy deviates from our strategy, then we set that strategy to be the myopic strategy for all previous times. So this leaves, since tau is the earliest time when the two strategies are different, this leaves pi tau unchanged relative to pi star at all times less than tau, and then only change it to PM. And then it's easier to look at to prove optimality of PM at that single moment of time. And then at subsequent times, we just choose p tau so that it is statistically equivalent to the old policy. It's also not so simple because you've messed up with the policy, but what you would do is, so rather than give a formula for what happens after time tau, I'll just say how we sample it in a way that assures statistical equivalence. So we take the history. The player replaces I tau by a choice I tau star sampled from the old distribution, because you want to. So you've replaced your distribution, your arbitrary min-max distribution, with this myopic distribution at time tau. But then as you're going forward, you want to somehow preserve the history of the old player. So so you would so if this so you sample I tau from that period using the old strategy. If the arm that is chosen are different, then G I tau tilde has not been observed, but the statistical equivalent quantity minus G I tau has been observed, because again, where the two arms are negatives of each other. So you could just look at, so sampling from one arm entails just negating the samples from the other arm. And you sort of, and so then you, at time tau, you just, if I tau, the index of the arm that has been actually chosen and the index of the arm that is chosen by the myopic player are the same, then you leave the sample unchanged. If they're different, then you just flip it. Okay, and that preserves the optimality of the min-max optimal strategy going forward. And then you would just iterate this proof. It's a finite, it's a discrete number of steps. So you've proved up to that myopic strategy is min-max optimal. Okay, are there any questions about this? Okay, so then from the optimality proof, we also see that the player is indifferent. I mean, everything is symmetric, so it's completely expected. The player is indifferent about which arm is risky. So this maximization is, in fact, for the optimal policy, gives us the same values of regret. So going forward, we could just label secretly from the player the risky arm as arm 1, the safe arm is arm 2, and emit this index J. So A is just going to be A1 and A2. A1 is the safe distribution, A2 is the risky distribution. Their means are symmetric around 0. Okay, so now we could use PDEs, and the main ideas for PDEs is numerical analysis in reverse. So we now have a discrete game, kind of like it's like a stochastic process. We find the the PDE that is discretized by that numerical scheme, or alternatively, you could think about that as the expectation of this martingale. So our state variables, you still have to do a little bit more work to get the state variable. So you have the variable eta that tells us how well the player did in that period. So why did we write it this way? Well, if the player chooses arm 1, then this quantity and one of these quantities cancel. So you have just the difference between G2 and G1. If the player chooses G2, then these two cancel, and then you have the difference between G1 and G2. This tracks the hidden gains, the gains that have not been revealed to the player, and this tracks all the revealed gains. So so we could also rewrite max over xi, where I is 1 or 2 in this form, and you could rewrite it in the new variables. So we get mu is the final value that in the new variables is the same as the max. Okay, so then we can set up a Bellman equation, a discrete iterative scheme. It's the expected final time regret achieved by the player if the prediction process starts at time t, given the state variable. So at final time, it's just mu. And then at earlier times, the value function today is the value function tomorrow, after incrementing all the variables in accordance with the rules of the game in expectation with respect to A, and this should be PM, the optimal strategy, not P. Okay. So this is d eta and dxc are represent reflect how the state variables are incremented if this game is played. So and the PD really comes from studying the Taylor expansion of this quantity. So you can have, it's not going to be C2. So okay, so let's so what is this PD? So U is a disk should be SC0 solution. Sorry, SC0 solution on this region. So we have 3 state variables now, 3 spatial variables, and negative times of ut plus lu equals q with the given prescribed final value. So lu is a constant coefficients spatial operator that comes from, again, Taylor expanding the right-hand side of 6b around eta, c, and t. And the stationary source term, which is epsilon if CR equal to 0, and minus epsilon if CR equals to 1, if less than 0. So this comes from the policy. So again, this operator, so this Q is obtained by comparing, by just looking at how V is incremented when the spatial variable that tracks how player does is incremented. Eta, since the final value of this expression, well, it's linear with a factor of 1/2. So you expect the solution of the PD also to be linear, and that's where we heuristically get the source term. But you can never get more than C1, but you could also get possibly C0 because of this discontinuity at CR. Yes.
So you said it's like a C1, C0, but then you have so those should be understood as weak derivatives, or
No, there's just not. These are just standard derivatives. You know, all the standard derivatives except at one point where they're undefined.
okay, this is the reason why it's C naught and not C.
Yes.
C infinity.
Yes, it's C infinity everywhere except in the region where CR is 0.
And there, what happens to the PD?
So okay, so you can actually solve this PD explicitly, and you get a parameter B that essentially parameterizes the jump in these derivatives, right? So you can, so it's so it's easier because the source is stationary. You don't even need to use Duhamel's principle. You can just use something more elementary. You could solve the ODE where the spatial operator is equal to the source term. So that kind of counts the contribution. Then you can, so that is explicit. You can, so here, this technique allows you just to put your contribution of the source term into the, to modify the final value of the problem.
But just to understand, so
Yeah.
your slide back to the PDE.
Yeah.
So this was about the source, right? But
Yeah.
just to solve the homogeneous problem is. you do
This-
the-
It's easy to, there's a fundamental solution.
okay,
so this is
you
a-
did the
this is a-
first order.
Yes, this is a constant coefficients linear parabolic PDE. So with appropriate change of variables, you just get standard fundamental solution of the heat equation. Okay, so this U, the solution of the PDE is also explicit and it's given by the convolution of this fundamental solution, which up to linear transformation of variables is the same as the solution of the heat equation, of the convolution of mu minus phi plus phi, okay? And so then we do backwards induction verification argument. So we initialize at the final time, they're both the PDE solution and the value function, they're equal. So our inductive hypothesis is that they're equal at t plus 1, and we guarantee that up to the discretization error, they're equal at all the early times. So we kind of propagate this backwards. So just to see this, the first equality comes from the PDE because U has been chosen as a Taylor approximation of this guy. So U is the Taylor approximation of this guy by the PDE solution. From this line to this line, we go by inductive hypothesis, and then here we go by the dynamic programming formulation of V, okay? And so you may ask, how is Taylor? I haven't done rescaling, so you could ask, how is the Taylor expansion useful in a game where the rewards are not small? But this G, because it's the fundamental solution of something that looks up to a linear transformation of coordinates, just like a heat equation, this G is just a function of C divided by square root of time. So when time is large, replacing C by C plus delta C, which is, has this fixed gains. So these two are only something like 0.1 of a square root of t apart. So in fact, when time is large, the changes in the function are small. Also, if you take third spatial derivatives, then the square root of t is going to come out. So you essentially get O. This should be minus. Apologies. This should be t to the minus 3/2. So you get this accumulation at the time step. Integrating with respect to time really leads to constant cumulative error from this term, and then this term, it has explicit. It's d order derivatives are just b, this parameter that we can choose, times epsilon d. So we can control the contribution of the stationary term to the error by controlling this b, and this is what allows us to optimize the error. And since I'm running out of time, I'm just going to say that you can do more or less the same thing. So what I did before was for regret. You could do more or less the same thing for pseudo regret, with just a simple linear final value and slightly different source term. So in the regime where, so I'm just wrapping up, in the regime where your gap is some constant gamma over square root of 2, your leading order term of the regret, so this is just the regret divided by square root of t, is the same as the PDE. So this is up to the discretization error, which I will talk about. So this should should be equal up to the lower order discretization error. I guess since I'm taking the limit, that actual error vanishes. So everything's correct on the slide. is equal to this guy, and from the explicit form of the PDE, this can be written explicitly. So we can plot the prefactor as a function of gamma. The dotted line is the pseudo regret. The straight line is the regret. You can numerically maximize them, so you could find the distribution. We could find the value of gamma and the value of epsilon that inflicts the highest regret, the highest pseudo regret. And you could also look at other gap regimes. So here epsilon scaled as 1/square root of t, but you could look at a small gap where epsilon is smaller, and you could see that in this gap regime, the regret is square root of epsilon times square root of t. So this is the same as just naively, you would get the same quantity if you just naively choose half of your arms, allocate them to one, half of your arms, half of your trials to one arm, half of your trials to the other arm. So this proves without resorting to information theory that in this regime, the gap is not detectable. Right? The player cannot do better than just splitting the population in two and pulling one arm half times in the other. And you can get also calculations for the larger gap. We have not been able yet to get all the way to fixed gap regime. We have some ideas on how to do it, but at the moment, these techniques do not work because the discretization error, the leading order term no longer dominates the discretization error if the gap grows slower than t minus t to the 1 minus 1/4. So in conclusion, we offer a fresh PDE-based perspective on symmetric two-arm bandit problems. We provide min-max optimality of the myopic player, obtain the leading order min-max optimal regret and pseudo regret with explicit non-asymptotic bounds. This improves the corresponding lower bound for the general two-arm bandit problem, and kind of one of the most fundamental problems. And we develop novel PDE-based techniques, which we hope could be used to investigate bandit problems further. There's more if you'd like more information. Let's see our preprint. Thank you very much.
Okay, thanks for the very nice talk, Vlad. Are there questions from the audience or from Zoom? Let me ask something. So usually with these problems, as you know, like you get nonlinear PDEs because you know, when you look at the optimal strategies, like the player wants to choose something that's perpendicular to the gradient to cancel the first order term. And this is not happening here, I guess.
This is not happening because the adversary needs to commit to the distribution of the arms up front. So so the reason you need to do it in the cases where the adversary can decide, can allocate the rewards in an adversarial fashion, there the player, if the player doesn't act according to the gradient, then the adversary can inflict the higher regret. But here the adversary is more limited, it needs to just commit to the distribution of arms in the very beginning. So this kind of optimization doesn't come up. In fact, instead you have to look more. So this is a more local computation. Here we have to look more globally. That's why it makes it so much harder than in those cases to see what is the optimal player. Another question? Yes.
So about the PDE, you mentioned that you can transform it to heat-like equation. So the fact that it has fourth order dispersion is like, it doesn't, I mean, fourth order PDE, second order, it's different, but it doesn't play a role here. This epsilon square fourth derivative thing.
It's not fourth derivative.
It's second order PDE. The highest derivative.
This is CH, CR. Okay. So, okay, so let me ask it in a different way. The fact that it's not, this was my second question. The fact that it's not isotropic in the different direction,
Mhm.
does it play a role? Does it say something?
Well-
Can we learn something from the PDE in that sense?
I mean, I don't know. I mean, the max function, right, is also not. I mean, it's just
I mean, in a sense, it has to do with how you define these variables.
yeah. You have to. You can
See-
convert it. You could do change your variables to more or less.
Right.
A
because it's
heat
second order.
equation,
So,
which
so I'm
will be
asking, do you learn something from this change of variable? Do you learn something from the
Well-
fact that it's not isotropic in the natural quote unquote?
Um,
Maybe no. right?
It's a good question. I haven't really thought about it. There's a more general story with these state variables that somehow when these problems are analyzed in the literature, they're not using the most optimal state variables for their analysis. So this what I think. So I think part of kind of the overall, I think, lesson is to really try to understand what is the sufficient statistic for the what is the best smallest state space where you could describe these problems. But I think when you change your coordinates, you can solve it explicitly through the heat equation. But I think in this formulation, you could see it's easier to see how it's connected to the value function.
Just that you get a change of, so maybe there are more natural coordinates for the problem now.
Yeah.
It becomes a vanilla equation. It's probably also, I'm asking, I mean, since you have epsilons, when you do the change of variable, then you get these epsilons inside the
Yes.
transformation
Yes.
matrix. Is it become like very imposed? Like because you have some change of variables and you take epsilons in some direction, in order ones in other directions.
Yeah, these are good questions. I mean, epsilons are important because if they are not small enough, then the error doesn't dominate the. But I think maybe there's more story to tell, and I think that's what we're looking at. How can you solve this when epsilon is? I mean, you need to modify it. I think some of the ideas would be to look at maybe optimal stopping problems. That seems to be the direction they've tried to take historically when they looked at these problems when epsilon was fixed. Kind of truncate your exploration period. Great.
There's a couple of questions on Zoom.
Okay.
So the first one, what is the practical value of getting the non-asymptotic bound?
Well, I think you give more robust guarantees. I mean, the idea would be if you wanted to use this in any meaning. So there's very limited use at the moment of these strategies in medicine. I know that in Greece they use Bandit algorithm recently to allocate COVID treatment, but overall the use of these has been very limited. So I think that any kind of practical use in the like critical settings like medical settings would probably necessitate non-asymptotic guarantees. I also think it makes this results more comparable to the results in the computer science literature, because there's a lot of, the previous results using information theoretic techniques were non-asymptotic, and so this allows us to obtain, compare apples to apples.
And the second question is another basic question. What are the non-asymptotic bound and asymptotic bound in the context of Bandit problem? Are they just the standard definition?
Oh, so when I say, asymptotic bounds, I just mean the bounds on the leading order term, on the constant of the leading order term. And when we talk about asymptotic bounds, we also quantify the error that comes from the higher order terms. Maybe I didn't fully understand that question. Yeah. So the PDE describes,
Yeah.
PDE captures everything up to the second order behavior in space and first order behavior in time. You have a discrete game, so you do truncation of your Taylor series, so you have to deal with the truncated terms, and this gives us those bounds.
Like when you prove an asymptotic bound, do you often have any idea of how large T has to be before it holds? And could this make it not practical?
No. Here, I didn't write it down. You could get all the explicit. So using our methods, you could get, I used asymptotic notation just to be able to fit it on the slide, but our methods will allow you to give not only the exact constants, but they can also give you exact constants in the error bound. So there's nothing unusual or large happening there.
Any other questions?
We have another paper, in fact, where we did on a different problem where we did go through the laborious calculation of nailing the exact constants. Also. So you could see that paper for how we did.
Okay, if there's no other questions, we'll thank Vlad again.
Thank you.
Thank you.